Good afternoon, everyone. Today, I welcome you to the second International Symposium on Application of AI in Metallurgy and Materials. So let me share you the screen. This is the second webinar on the weekly webinar, and this is webinar 2, Alloy and Process Design using Artificial Intelligence or AI. So today we will have 4 speakers to give us a insight into the application of artificial intelligence in metallurgy and materials, and especially in the aspect of alloy and process design using the AI. So first of all, I would like to introduce the organizing committee and our chair and co-chair of this symposium. It's his first series of this. The first symposium is actually organized by University of Science and Technology in Beijing, and this is the second symposium of the international meeting on application of artificial intelligence in metallurgy and materials. The symposium chair is Professor Hong Biaodong from University of Leicester, and the co-chair is Professor Jianxin Xie from University of Science and Technology, Beijing. And I'm a chair of organizing committee, and we have Jenny as a co-chair of organizing committee. We have Andrew Dunsmore, an organizer, and Dr. Hua Dongfu from University of Science and Technology, Beijing, and last but not least, our conference manager, Risha Jadeja, and from University of Leicester. So the previous webinar on application of AI for material science engineering attract a lot of attention for the community to actually realize about the application of AI in metallurgy and materials, and it's given by Professor Harry Badesia and Hong Biaodong on the topic. And today we would like to introduce our 4 speakers who is actually Professor Ian Crispy, Pro-Vice Chancellor in Research and Enterprise from University of Leicester, and Professor Jian Yang, a Professor of Material Science and Tech Engineering from Shanghai University, and Dr. Richard Curry, Program Manager from Swansea University, and myself, Chinapat Panwisawas from University of Leicester. So the program of today's webinar, we will have, firstly, we will start from the keynote talk by Professor Jian Yang from Shanghai University on the topic of development of artificial intelligence methodology technology based on big data. And our invited talk by Dr. Richard Curry from Swansea University on the topic of digital manufacturing within sustained future manufacturing research hub. And then last but not least, I will give talk on the computational material science of metal additive manufacturing from fluid dynamics to digital material design. And then we will start our panel discussion, basically a Q&A session at the end of the webinar. So if you have any question, please feel free to leave your question in the question box and indicate who you want to answer your question. So may I introduce Professor Ian Crispy. He is a Pro-Vice Chancellor in Research and Enterprise at University of Leicester, who would like to, he will be the person who give a welcome speech to everyone here. So may I introduce Professor Ian Crispy, and then thank you very much indeed.
of the blowing, we should charge a lot of raw material into the converter. So it is a rather complicated process. So, and we should to develop some automation and operations and to master this process. And we have developed one key BOF steelmaking technology, and it is include the automation control system of the oxygen blowing and the lens position and the bottom blowing and the raw material weighting and charging and substance measurement and the convert mode technology and to develop one key BOF steelmaking. So, and for the conventional BOF blowing, we used the 147 keys, and we just can use one key and for the operation of the BOF steelmaking now. And for the IH refining automation technology, we also must develop automatic control of the argon gas blowing and the top lens system and the vacuum system and the ferro aero addition. And we also have to develop the IH co-motor. And for the top lens system, now we can use the one key. And for the argon gas system, and it is also key free. And for the vacuum system, it is also just one key. And for the ferro aero system, it is after calculation confirmation, we can use also use one key. And the IH co-motor for the motor and error for the real-time temperature estimation and the dynamical decarbonization motor is quite accurate. So the future direction of the IH refining is develop the one key IH. And about the optimization of the rolling process parameters, and based on the CPS systems of multi-process coordinated control in rolling process, and the mechanism, multi-process dynamic coordination matching. And it is about the real-time forecast technology of the cross-section temperature field. And it is also about the multi-process shape presetting and comprehensive matching control technology. Also about the integrated control of the hot rolling, cold rolling, and continuous casting annealing. So for the steady state process, we can develop the accurate quality control. For the automatic control of the thickness, for the width, and for the shape, for the friction rolling temperature, for the cooling temperature, for the combustion in the furnace. And for the unsteady state process, we can also get the accurate quality control. And for the head and the tail short stroke control, for the dynamic setting control, for the intelligent control of the plan shape, for the adaptive control of threading, for the wide direction temperature control, for the dynamic control of strategy. And about the artificial intelligence in material design, and and the property of the materials is determined by the microstructure. And the microstructure is also determined by the compositions and the process of the matters. So, and it is the inherent laws of the materials are very complicated. And so this process should be optimized by the artificial neural network. And for the required properties, we based on the database, and we get the evaluation, and from the artificial neural network, and from our knowledge, and we make this verification. So we can accelerate the design of this kind of materials. And for the optimization of the material procession, and for example, we use the artificial neural network to assist in the optimization of the producing process, and for the conventional one and for the optimized one, and we optimize the annealing temperature, annealing time, and the solution temperature, solution time, and so on. So we can get much different or much better and the well surface morphology of samples. And we can also get the fracture surface of the impact samples. And the impact energy is improved from 29 joule to the 42 joule. And the second part of my presentation is about the development of AI metallurgy technology based on big data. And firstly, about the prediction of the KR and Canberra reactor desulfurization endpoint. So the problem is the low prediction accuracy of the desulfurization endpoint results in low production efficiency and high production cost. So to solve this problem, we use the AI technology and combined with big data to make the prediction of the desulfurization endpoint. And the intelligent optimization method of the desulfurization process was developed. So we use 3 kinds of the model. The first one is the multiple linear regression model. The second one is the artificial neural network model. And the third one is the simulation annealing particle swarming optimization. So it is these 3 models. Use these 3 models, and we can make the prediction of the KR desulfurization endpoint. And here is the KR process. And you know it, and there are impeller, and with impeller inserted into the hot matter and the rotation, rotated and to stir the hot matter and the slag. So they can mix the slag and hot matter and to desulfurize the hot matter or remove the sulfur from the hot matter and the flow up to the slag. So, and it is the industrial data analysis for the endpoint of the sulfur content, and it is influenced by the lime weight and also by the hot matter sulfur content. And here is the endpoint prediction and error analysis. And we use the correlation coefficient and the mean absolute relative error and the root mean square error to evaluate these 3 models, which one is better. And it shows that the sulfur ANN with the highest and the correlation coefficient and with the lowest the mean absolute relative error and the rule mean square error. So this one is the best one. And from the error box, you can also see, and the third one is the best one. So we use this model, the simulation annealing particle swarm optimization model, to predict the effect of the process parameter on KR desulfurization ratio. And here is the effect of the hot matter sulfur content, line weight, and the hot matter temperature and the weight on the desulfurization ratio. And with increasing the hot matter sulfur content, the desulfurization ratio is increased. And with increasing the line weight and the hot matter temperature, the desulfurization ratio is also increased. And another one is the prediction of the line and desulfurization ratio of the KR and based on big data, the line and utilization ratio. So the power plant is in the KR desulfurization process. Line is easy to agglomerate and the resulting low line utilization ratio and high cost. And to solve this problem, we based on the industrial data and the artificial intelligence and make the prediction of the line utilization ratio. And to optimize the desulfurization process and determine the addition amount of the desulfurization flux. So in the desulfurization and with the lime, here is the reaction. The lime oxide plus the sulfur plus carbon to produce the lime sulfide and the carbon oxide. So we use 3 modes, and one is a random forest. The second one is a support vector machine. The third one is a convolution neural network. And we use, at first, we make the data pretreatment. And here is a correlation analysis. And the one to the yellow color is a positive correlation. And the one to the blue color is a negative correlation. And the size of the cycle means the strength of the size and the strength of the influence. So, and at first, and we should use the Pearson correlation coefficient used to identify if the variables have the great influence on the line utilization ratio. And the process data of KR and the desulfurization is one-dimensional and discrete. So convolution neural network cannot be used directly, and it requires the transformation of the data. And we must transfer this one-dimensional data to this two-dimensional image. And here is a comparison of the prediction accuracy for the 3 models. And you can see, and from the R, the correlation coefficient, and the third one, the convolution neural network, and has a better and accuracy for the prediction. And here is a comparison of the model prediction error. We also use the mean absolute relative error and the rule mean square error to evaluate these 3 models. You can also see the third one, the convolutional neural network, has the lowest error. And the error box, it is also the best one. And is the error distribution, the third model is also the best. So we use the third model and the convolution neural network to analyze the effect of the process parameters on the line utilization ratio. And here is the sensitivity analysis of the process parameter. And the initial sulfur content and the amount of line weight are the main parameters affecting the utilization ratio of line. And here is a factor of the line initial sulfur content and the line weight on the line utilization ratio. And with the increase of the initial sulfur content, the line utilization ratio is increased. And with the increasing line weight, the line utilization ratio is decreased. And okay, and I'd like to show you the tensile strength and prediction model of the X17 pipeline steel. And the pipeline is the X17 pipeline steel has a very strict quality requirement so that it is difficult to control the stability of the tensile strength. So to solve this problem, we use AI technology and combined with big data and to make the mechanical property prediction and to compare various modeling techniques and to find the optimal model. And this time we use the 6 models. The first one is the Bayesian regulation network. The second one is the radial basis function and neural network. The third one is the stepwise regression. The fourth one is the rigid regression. The fifth one is support vector machine. The sixth one is the random forest. And here is the tensor strength and the prediction model of the X17 pipeline steel. And about this 6 model, and the 6th one is the best one. And the artificial intelligence algorithm is better than the multi-linear regression algorithm. And the random forest performs the best, and with very low error distribution, narrow distribution, and very small error. And I also like to show you the prediction of the impact energy of the low carbon steel. And the problem is the impact testing is a time consuming and labor consuming and high cost. And the ability of a shallow neural network is limited to fit some complex relationship. So the solution is a mechanical property prediction model and based on deep learning technology, and to find the high accuracy mechanical property prediction technology to assist the process design. And this time, we developed the 16th model, and it is divided into 2 groups. One is a shallow neural network, and the second group is a deep neural network. And here is a modeling data distribution and about the carbon content and the silicon and the manganese and sulfur phosphorus and so on. It is the modeling data distribution. And at first, we must do some data pretreatment, and the data normalization was done, and also the data equalization was also done. And we convert the data into a more balanced data by the log calculation. And all of the data was randomly and divided into the 3 groups. And into the training data, into the verification data, into the testing data. And here is a determination of the optimal parameters of shallow neural network. And we can determine the number of neurons in the mid layers. And for the highest spot, we can get the best number of the neurons in the meta layers. And to determine the activation function, and this is the activation function, the second one, and the third one is the training function, and to determine which one is the best one. And it is judged by the correlation coefficient. And we also judged based on the mean square error, we can also make the same judge. And the result is the same as formula 1. And here is a comparison of the prediction errors of the different 16 different models. And the prediction accuracy of the deep neural network is higher than the shallow neural network. And this DNN is a deep neural network, and the ANN is a shallow neural network. And the deep neural network optimized by the Bayesian, and this one 16th, has the highest accuracy with the smallest error box, and with smallest and this error. And here is the sensitivity analysis of the process, and based on the Bayesian optimized deep neural network. And for the low carbon steel with the thickness of the 7.5 millimeters, the original snap thickness, and the rough rolling temperature, this one, and the intermediate snap thickness, this one, have the obvious effects on the impact energy. And here I show you the using the semi-supervised learning to improve the prediction accuracy of the steel properties. And the problem is that the mechanical property test of strip steel is sampled for inspection, and data of some steel grade is insufficient. So to solve this problem, we make full use of unlabeled data. And the unlabeled data is a data and just has the information of the compositions with the process parameters, but without the information of the properties of the materials. So we make full use of this unlabeled data combined with the semi-supervised learning method, and add pseudo text to the data and expand the data set. So, and we use the deep neural network model combined with the semi-supervised learning. So in this study, we compare these two models. One is Borden, is a deep neural network optimized by the Bayesian. And the second one is safer Borden, is a deep neural network optimized by the Bayesian and semi-supervised learning. So, and in this one, in the Borden, we just use the training data, only the labeled data. In the safer Borden, we use the training data and use the labeled data and the unlabeled data with the pseudo label. Here is a comparison of the prediction accuracy of the different model, and absolute relative error and the mean square error to judge and to evaluate and which model is better. You can see the red one is safe Borden. So, and the error for the safe Borden is lower than the Borden. and the error box is smaller than the burden, and this arrow is also smaller than the burden. So this one is better. And here is the comparison of the prediction accuracy of the different model. And you can see from the correlation coefficient and the second model and the prediction result of the safer burden is better than both model. And the last one, I'm gonna show you the materials and the constitutive equation. You know, the constitutive equation, it is very useful to study the mechanical behavior of the materials and to predict the deformation resistance of materials and to determine the rolling force. So traditionally, we use the mathematical method, but it has drawbacks such as the large amount of calculation, and it is very difficult to determine the optimal parameters. So, and in this study, we use 4 models. The first one is the Arrhenius type equation. The second one is the parameters optimized by the genetical algorithm. And the third one is the parameters optimized by the artificial neural network. And the fourth one is the prediction error of the traditional constitutive equation optimized by the genetical algorithm. And here is the result of the material and the constitutive equation and comparison and of the correlation coefficient and the mean square error and the mean absolute relative error. And you can see the artificial neural network and has the highest accuracy, And for the modeling operation, the optimized genetical algorithm is and highest and modeling operation. And okay, and I'd like to conclude my talk. And for the development of the artificial and intelligence metallurgy technology based on the big data, now on steel making, for example, the KR desulfurization, converter blowing, and the edge refining and the ELF refining. And we can do some about the continuous casting and about the surface defect of the automobile exposed panel, about the surface crack of the thick plate, about the center segregation of the thick plate, about the slab continuous casting and the billet continuous casting, and about the rolling. The AI metallurgy can also deal with the rolling force setting and the optimization of a rolling process and the optimization of the cooling process, optimization of heat treatment and the mechanical property prediction. And about the AI metallurgy for the materials, we can do component design, phase change design, microstructure design, relationship between the microstructure and the properties, and the mechanical property and the design. Okay, that's all for my presentation. Thank you for your kind attention.
Thank you very much, Professor Yang. I would like to ask anyone, if you have a question, can you actually type it in the chat boxes, and then we will pick up your question. I mean, in the panel discussion. So every question will go to the last bit. So that the next presentation will be given by Dr. Richard Curry. Dr. Richard Curry is the Sustained Research Program Manager based at University of Swansea University. And Richard has his background in electronic engineering, biomedical sensor, and holographic lithography. And now Richard will give us some perspective on the digital manufacturing within the sustained future manufacturing hub that he's actually managed. And please, the floor is yours, Richard.
Thank you very much, Chinapat. I'm just trying to share this screen.
Yes, please.
Can everybody see that? Well, can you see that?
Yes, yeah, I can see your screen. If you can put it in the presentation mode, that would be great.
Yeah, there we go. Excellent. Right, so what I'm going to do is just give you a quick introduction to what Sustain is, and then go into some detail on the digital side of the work that we are doing. It's quite early days in the project, so this, it's not going to be, there's not going to be a lot of really good, results and things to talk about. It's going to be more about the methodology that we're taking and where we're getting to. But before we get to the digital, I just want to give you a quick overview of what we are and what we do. So, it's a UK-based project. Through our research council, EPSRC, and it also has the top 5 by volume steel companies within the UK as part of the consortium. And the importance of UK steel for UK manufacturing is paramount. I've put some numbers up there. It might be quite small numbers for for people in China, but in the UK and in Europe, these are quite large. Not that the UK are really a manufacturing country like we used to be, but we still do have our manufacturing industries as well. So just to give an overview, as everyone knows, steel is very important. 75% of the grades that we use today didn't exist 20 years ago. The amount of steel used globally, it's roughly 200 kilograms per person. There isn't anything that we use that doesn't incorporate steel, and steel is very important for the future in terms of electric vehicles, in terms of every industry really. But we've got to work to bring down the CO2, and we do that through various technologies, and obviously one of those very important technologies is digital. The UK is in a bit of a climate crisis, as is the world, and in the UK we've basically just been outsourcing rather than actually doing real carbon capture and storage, or looking at the problem, which is something that we're really taking seriously. The energy crisis in the UK is growing. As we shift more to renewables, we need to really make some decisions about how we're going to power things like the land transport, freight, how we're going to do domestic heating and various things. There's a waste crisis globally at the moment, and as you see on this quick chart here, it's quite clear that the more developed and industrialized a country becomes, the amount of waste that or the resources we use increases. And we need to do something about waste, and we need to start, thinking about circular economies and reusing things, and not just throwing them away and landfilling. Sustain's part of a series of projects, including Comet, the Rapid Alloy Prototyping Centre, the Active Building Centre Specific and Sunrise, that are across the Swansea University and Warwick University, and each has its own part. And we're looking at various things such as, using photovoltaics and various other technologies for active buildings, which would power themselves and also supply the grid. So we don't just have point sources of power, we distribute the power. Specific looks particularly at the renewables, and Sustain is really focused upon steel and how we apply some of these things plus new ideas into steel. The project itself is, as I said, it's a collaboration between Sheffield, Warwick, and Swansea, and we also have other companies such as MPI, the Royce Centre, which is at Manchester and Sheffield, and various other technology centres involved. We also engage with the UK Steel for government lobbying, policy, that sort of thing, and we work with community and various other unions because we're also concerned about the people aspects and making sure that everything we do is sustainable, not just in terms of the product, but in terms of the people as well. Just a couple of slides to sort of to give a bit more of a picture there. We're really driving the low TRL levels, the bright ideas, to then feed into other UK initiatives such as industrial decarbonisation, made smarter. You can read them there. But basically, Sustain is about developing bright ideas that can then be developed on the TRL scale and then be commercialised and actually make a difference to the industry. So Sustain is basically split up into two grand challenges. One is carbon neutral iron and steel making, and the second is smart steel processing. And within these two areas, we have a series of themes and a series of projects or tasks where we actually we look at various key aspects of either process or technology and bring that into steel. So you can read them there. I'll not labour on that. I'm going to quickly go through some of these and then get into the interesting stuff for you guys, which is the digital stuff. So we're looking at creating a CO2 value chain in the first task. We're looking at emissions and how we capture those emissions, how we separate them, and how we turn them into new products. So, capturing the CO2, separating out all of the nasties that either would pollute the product or cause issues with the separation and catalysis and things. And we are looking to produce things like polymers, dyes, pharmaceuticals, fertilizers, and proteins, various things from the waste emissions. We're also looking at reusing waste. So as you saw on a previous slide, there is there's a plastics crisis within the world. We've got far too much plastics being not just landfilled, but dumped in the sea and various other places. This plastic could be reused if you had the suitable carbon capture and storage on top of the furnaces to then take that away and do something positive with it. So we're not just emitting it as CO2, and also providing energy rather than fossil fuels that we then obviously have to dig out of the ground and use for the process. We're looking very closely at scrap or recycled metals, and looking towards not just reusing these and downcycling them for low value products, but how far can we go in terms of using 100% scrap and creating the high value strip grades and various other grades that that we need to make. We're looking at doing this in a way that is circular economy based, and hopefully within the next 10 years the UK will be self-sufficient in terms of the recycling of our metals. We also look at thermal efficiency. So this is basically not just the recycling and reuse of refractories, but extending the life. And we're also looking at key technologies for I guess what you would call thermopiles, for using refractories as generators. This could be to actually provide low level electrical energy for the plant, or it could be to power remote sensors and various things like that. Task 8, which is based on looking at sensors. We're looking at new sensor designs, high temperature sensors, and also novel sensors to look at things such as the change in the phase or the grains between the different the metals that we're producing. So we have the feedback on the furnace and in terms of temperature and speed and various things, so we can actually have much more of a control over the product than we currently do. And the final one I would quickly go through is looking at late stage definition and integration, how we can basically reduce the amount of alloying that we put into metals, and can we use very similar feedstocks but then differentiate at the end of the process. So this is really good because obviously you're not putting those extra alloying elements in there, you're not doing separate processes batch for different materials. through the process. And also we're looking towards the recyclability of these materials. So the more you alloy a material, the more difficult it may be to recycle that for various different uses. Right, so with that out of the way, I'd like to just tell you a little bit about tasks 4 and 5, which focus upon the Digital Steel Innovation Cluster. And this is all about looking at the supply chain. We're really looking at digital twins for the supply chain, not just for interest or data, or we're actually looking at how we can model these things so we know what the properties are going to be like, or if there are going to be any issues in the process. This will all come out through the modeling. We're looking at end-to-end supply chain productivity as well, new business models, disrupting supply chains, new product fingerprints, connected steel products. We're looking at various technologies such as blockchain to almost sort of police the steel, so you've got confidence and trust that the steel that you purchase has emitted X carbon or below a level of carbon dioxide, or how much energy has been used to make that, and then using key identifiers to make sure that you've actually got something that can go around the cycle, ad infinitum, without losing track of where the various products have originally come from. We're also looking at data capture sensors, Internet of Things, to bring together the plants and to have much more information about the products that we're making. So the Digital Supply Chain Innovation Centre looks at bringing together the capability-driven projects from academia and the problem-driven projects from industry. The whole process is it's starting from scratch, getting the guys around the table, developing the ideas through regular workshops, ramping them up almost in a similar fashion to Google Sprint, that sort of thing, for developing ideas, testing the new minds into the results into the rest of the industry. So the methodology for this is laid out here. It's all about sort of monitoring, reflecting, looking at the impact and the goals of what we do. Of course, we're looking at zero waste, carbon neutral line steelmaking, and smart steel processing, our 2 grand challenges, and then feeding them through, looking at what the potential outcomes could be, what the short-term outcomes could be, and then actually targeting the stakeholders and developing the outputs through that. We're doing this through 2 PDRAs based at Warwick and a 3rd PDRA researcher based at Swansea, and we're also bringing in MSc students as well. Plus, I think there's 1 or 2 PhDs are currently associated with this project. So, progress to date, as I said, we've just really set this up. We have, in the supply chain side of things, we have done a little bit of development. COVID-19 and all of the issues around that have slowed us down somewhat as well, because a lot of the UK plants have gone on furlough, but we've still sort of pushed on, and we've managed to do quite a lot given the remote working and ensuring we can actually interrogate the systems and also talk to the guys who are on the plant with the problems. So we're developing new technologies based on deep artificial neural networks and probabilistic models for sequential decision making with applications in smart steel processing. We're using historical data repositories as well, which we've got full access from across all of our steel makers. In the UK, we have a complementary steel making industry. We don't have 2 plants that make the same thing. So we do have a lot of data from a lot of different areas for a lot of different products and a lot of different processes, which we're feeding in, and we're really starting to build some very strong models on each of the processes, which are obviously from strip steel through to longs, speciality steels, and construction. We're looking at novel reinforcement learning methodologies as well, and we're hoping this will be instrumental in delivering an AI system that's able to automate and optimize certain processes that currently, especially in the steel industry, rely heavily on manual intervention. So moving on from that, we're looking towards developing sort of a two-phase process, looking at demand, supply and inventory process for the supply chain with enabling inhibit analysis and demand profiling. The second phase is looking at integrated planning and process design, and then modelling of the potential benefits within the supply chain. And then we're looking at the pragmatic method for the future that we agree with the companies that we're working with. I'm just moving on quickly because I know I've got a little less time than originally I had it. So the second project is task 5, where we're looking at through process models, and this is all about trying to develop models that are that we're able to run very quickly, rather than very large, very complicated models that require significant amount of computational time. So both Richard Thackeray and Michael Howing are looking at methods for I guess picking out the key variables within each of the processes that we're looking at, and then using things like machine learning and AI to assist with with some of the variability. So it's about fast computation to improve performance and to verify the accuracy. The through process models are for inline optimization, identification of bottlenecks, and to link between individual processes. And then the process optimization side is looking at to generate databases, verify the accuracy of the predictions, and to optimize the production of the plants. So basically, there's been many attempts in the steel industry and in academia, in the UK and Europe, across the world, to do descriptive numerical and analytical computer simulations of many of these processes. And many of them are very complex, and you're unable to actually run them in real time, even with today's computational performance. So there's a hand raised. I don't know if are we taking questions through the presentation, Chinapat?
We're going to do questions at the end.
Okay.
Yeah, we'll take the presentation at the end. Yeah.
Yeah. Okay.
If anyone, have you finished your presentation?
Not yet. Got a few
not yet. Okay.
Slides. Yeah. I'm trying to get through as fast as I can for you, just to make up a bit of time.
It's okay. It's okay. Yeah.
Right.
Take your time. Yeah.
Thank you. So, as well as doing the work that I've just described, we're also looking at the sort of LCA analysis side of things as well. So we're not just we're actually joining up the loop, and we're making sure that what we're doing is actually low carbon emission, low energy. We're trying to reduce the impact of carbon, and also the energy used on the process, and other things such as other resources such as water and various other things. So ultimately, with these things put together, we're hoping that in a year or two we'll have a coherent process level model for fast and efficient optimization. So here's a few examples of things that we're working on currently, which include a model of the blast furnace, and we're looking at cooling behaviour of porous media as well for macro micro coupling of heat transfer. So to conclude, we are basically trying to turn the whole thing of steel being a problem, which it sometimes is seen as being in the UK and in Europe in terms of the carbon emission. And we're looking at how steel, because of its complexity and because of all of the various routes that are within steelmaking, how we can turn that into a solution rather than a problem. And this last slide just basically looks at the way all of the different tasks that I've gone through very quickly link together and actually help to use the steel industry to solve some of the issues that we currently have within the UK. Thank you very much.
Thank you very much, Richard. And as I said previously, if you have any question, please type it in. Please type it in the Q&As or chatting box or Q&A boxes that we will pick up in the panel discussion. So from now is actually myself. Let me introduce myself as well. I'm Chinapat Panvisawas. I'm associate professor in digital manufacturing and also associate director of NISCO UK Research Center, where Professor Hong Piao Tong is the director, and also I'm a EBSRC UKR Innovation Fellow. And today I want to give you some insight in the computational material science of metal 3D printing or additive manufacturing, from the kind of first principle calculation, but in a micro scale, to how can we say about digital material design. And this one will bridge across the length scale from the, actually the previous two talks is fantastic, that give us some big picture and also some specific process from the first talk from Professor Yang, and give us some idea how can we use AI in the high level still making process. And also from the Richard point of view, they will give you some more idea about management side, and then how can we bring across the knowledge from the laboratory to the real practice. And now I'm talking about what is actually happening in the very low length scale, and this is about my talk. So the thing I want to say first is that when you want, my experience in the past 12 years or so is on this aerospace material. I'm busy thinking about what is the material behavior look like in the very small scale. And this actually, when you may have heard about this kind of from atom to jet engine. So we design something from the very in atomic scale, and this atomic scale knowledge will give you some design in the component level. And this is very important that material scientists will use this knowledge to whatever you will use AI as a tool to accelerate this kind of acquisition, knowledge acquisition or whatsoever. But my talk today will focus, my key point today is that successful adoption of the digital technology, whatever you use, casting, welding, or even 3D printing, to aerospace application is actually largely based upon the fundamental understanding of the material processing to develop, kind of AI or machine learning algorithm for future material and process design. This is about what I'm going to talk to you today. The challenge, if you talk about the how to say, the exciting digital technology called metal 3D printing, you may know that there's various approach or technique that you can do 3D printing. One of which is actually direct laser deposition, that you actually deposit the hot metal, melt hot metal into your substrate, and then actually the thing happening at the very low length scale. If you zoom in, you will see that you see liquid metal moving, and then see something coming out, a kind of vapor pressure, metric vapor, which coming out, and this actually will govern a lot of property later on. Another, the technique and also simulation result that people trying to do. This is the data published recently in 2020 in digital in additive manufacturing. You will see that the detailed information of this micro length scale, about 100 micron here, can give you insight in the technology. How can you improve it? And today the talk I'm talking today will focus on the 3D printing technique, so-called selective laser melting or powder bed fusion additive manufacturing. That if you understand the processing science at the very low length scale, you will understand what is the emerging microstructure and hence the property and performance. the research interest that I'm interested in the past 8-9 years or so is on the computational material science and engineering using the integrated computational material engineering approach. So to simulate the liquid metal that I mean using the thermofluid solute dynamics technique, and this will apply to latest advanced manufacturing processes like investment casting, laser or electron beam fusion welding, and lately digital manufacturing. So if you look at what is going on in the millimeter length scale, you will see that the fluid dynamics, and now the fluid here is a liquid metal fluid. And then you will see that a lot of things going on is not as simple as you thought at all. And this, how can we simulate, or how can we actually predict it somehow in order to say about the signature that we can bring out from this kind of phenomena to influence the design at the end. So this is our first study back in 2000, probably 14, 15 as well. So we are looking at the edge of the well plate. So we can assume that this is 100% packing density, and then we look at what is the interaction of the heat source and the materials. And the model here try to capture the solid liquid interface that is going on, or you may also call keyhole formation using the high-speed camera. And this kind of in situ observation, or someone will call it I mean a process modeling approach here, will give you some kind of validation of your model, whether your model is correct or not. This is in order to apply this to more complicated processes like metal 3D printing. And all of this, you have to deal with some mathematics, computer science, and hence physics. And I mean, this is some kind of a set of equation that you can find also in my publication in 2018 on how can we actually solve and go about it. And the reason I mentioned about this, because when you decide the additive manufacturing for specific application, it's not because it's not actually you want to actually determine the property of performance that you want, and then you will get the final product like you want. But you have to understand what is the processing science look like, and that will influence your emerging microstructure and hence property. Is another way around from the previous design principle. So we will say that in this presentation, I basically use a science push approach to go about design the metal 3D printing. And definitely, as a material scientist or material engineer, you know that we're talking about four strands of materials, which is a material of composition, process, structure, and the property. How can we link all these four together? And for additive, it's quite unique from other process. I will let you know why it's a bit different from other process. So first, I want you to look at the real time video doing the direct laser deposition, actually taken from at University of Birmingham long time ago. You will see that a lot of things going on. The melt pool here, this is a liquid metal. The melt pool is it's not very large, I would say. It's maximum in a millimeter length scale. This is just 200 micron scale bar here. And then the thing you will see that from this video, you see a lot of phenomena happen here. Gas, liquid, solid interaction, spatter, vaporization. You see a vapor plume now. And then hence emerging microstructure, dendritic growth or cellular growth or whatever. This need to be understood. This is in order to predict the final mechanical property. And let me explain a little bit more on this. Lately, people trying to visual what is going on in a bit more detail. I mean, more in the spatial length scale. And then you will see that if you use a X-ray synchrotron to look at what is going on during the process, you will see that there are a lot of things going on here, including, I mean, if I summarize on the right-hand side, compared with the high-speed imaging here. You have particle dynamics on the left-hand side when you have a gas expansion. And definitely one of the most complicated that induce most of the thing is a thermofluid dynamics behavior during the processing as a function of many things that I will mention next. And subsequent the solid state transformation. I mean, solidification, rapid solidification, rapid repeat solidification behavior. And hence the solid mechanics will be very unique because of the cooling rate of this process is so extreme. Okay, well, how can we go about that? The first thing is to how can we actually get an idea of or first simulate what is going on during powder bed fusion additive manufacturing. So this is an example that you may, if you simulate this, you may go to the two different modes, which is called conduction mode and keyholing mode. The conduction mode will just fuse the powder together, and the keyholing mode will create some hole during the deposition, and hence probably defects or something that people want to avoid. So this model that I developed some time ago can actually capture those phenomena, the first two. Another thing is that apart from the material behavior itself, about the laser, how to say, physics or operation mode is important as well. This will influence your thermal fluid dynamics significantly. So you need to simulate this one quite carefully of the interaction in the 100 micron length scale, for example. And this is give you some three scenario of that. And the next thing is, apart from those two, another thing is the alloy dependent. If you have two different property or two different materials, you will see different behavior of the melting process during the additive manufacturing, like this one. I mean, this three slides give you some kind of an overview and example how complicated of the metal additive manufacturing look like, and I summarize a kind of physics that are going on in the process, because in order to build AI, we may need to have knowledge to tell the algorithm what we are going to actually simulate or been predicting. And the powder particle dynamics, as I said, phase transition, and then link those lower length scale information to the higher length scale to predict the property, and hence the solid mechanics and defect formation like cracking or residue development. As I said, the nature, why we need such a very high fidelity modeling to look at this process, because we have this additive process is quite stochastic. So you can't actually give one condition to the one people in the one machine and you get the same answer. It's impossible. You need to understand the process of this is actually is random. So you need to have a tool that allow you to give some statistical prediction. What is actually happening in a acceptable length condition, and this gives you some two example of the two different behavior of different process parameter, which is layer thickness and scanning speed. Give you totally different surface and subsurface porosity level, and this has to be understood. And how can we predict that? This is the question I want to ask. And after the deposition, you may want to say that, okay, how can we know this is good or not? We need to see an overview, much bird eye view. And this is a kind of study that's looking at the effect of processing parameter to the porosity level. You will see that if we vary the process parameter carefully, we can avoid a kind of cheese-like structure on the right-hand side here. And how can we do that? First, we need to understand what is going on in additive. I don't want to go much into the deep detail, but I just want to emphasize that additive has a kind of rapid and repeat cycle, heat cycle, like on the left-hand side here in the yellow shade. And you will see that if you see this curve carefully, you know that the material is subject to kind of melting and remelting at least 3 times at the same position. So and another thing to mention is that this is a rapid cooling process. So it can be 10 to minus 5 to 10 to minus 7 centigrade per second. So how can we actually understand this extreme physics, and also to understand the emerging microstructure and hence property that we can design or optimize for our specific application. So the tool that I used in the past many years is the integrated computational science. So we need to link information. The key here is to link information from the lower length scale to the higher length scale. And this can be done by not only experiment, but also you have to talk with some modeler as well. For example, the hierarchical microstructure. I mean, probably I start from powder dynamics. When you have a powder, the powder quality is so influenced into the final product. And this one, definitely the link of powder to the microstructure is a processing, which is, I call it thermofluid flow or thermofluid solute flow. And this is the length scale that I'm looking at. And hence you will see different in the microstructure by varying the key process variable that I mentioned earlier. And this is the kind of focus of my work in the past many years. And this information will be used and useful for the AI in the future. It's kind of, how to say, the knowledge that you use to train your model. And I start from the powder particle measurement using laser, and then I fit the powder particle, arrange it in the bed, and then simulate the kind of spreading of the powder in the powder-based process. And after that, I spread the laser beam, and then looking at what is, make sure that I capture all the physical phenomenon happen during the process. And hence we want to actually to use this model to predict something like porosity level. This is an example that published in Computational Material Science using titanium-64 materials. And then you see that the single track experiment match quite well with a modeling result here. On the right-hand side, you see the modeling result, which has a good agreement with the experiment in terms of the porosity level. And this one can be done using the distributed powder particles. So we can't avoid distribution, both shape and size distribution of powder, to actually give some meaningful prediction for industry, because porosity is one of the critical things that metal additive people want to know. Apart from that, lately, if you want to do additive manufacturing, another thing you concern is about roughness. Some paper lately say that you need to have the resolution of about few micrometer length, resolution. If you have too big roughness, this may not be used in the real application. So how can we go about roughness? So one of the way we can do is use this type of high fidelity model to give you some insight what is actually happening, whether you will get balling effect or not if you use this process parameter. This is an example that give you insight in the nickel-based superalloy 718. And something you see in 2D, probably not real in 3D. This is another thing this slide say to you. Something, if I look at from the top, I may not see a kind of balling effect like this. I just see some discontinuity. But some track is look perfect on the top view, but it's not when you do 3D tomography. And this kind of thing has to implement or actually attach with the 3D printer. These days they are talking about in situ or lab scale or tomography to check your final product. Another thing, once we actually successfully understand the melt pool dynamics, we can use the information to go further the length scale to predict the grain growth behavior, for example. and this one, if you carefully selected or simulate the condition, you may see that the high fidelity model can give you quite good agreement with the experiment. I need to wrap. Is it about few more slides? Another thing is that concern metallurgists is the phase transformation, especially solid transformation. So precipitation is actually so important to govern your mechanical behavior. For example, in nickel-based superalloy or titanium alloy, a two-phase structure, you want to know about the precipitation content or secondary phase content that actually embedded in your final product, because this will give you whether or not this will fail during service. And because the spatial signature of thermal signature that I mentioned earlier, that gives the distribution of this secondary phase not homogeneous. I mean, as printed condition, like the prediction here, she's published in ACTA 2018. And then you will see that if you carefully simulate this, you can have a process window for industrial to use. And then you can do AI later. And last but not least, I would like to summarize all this in this diagram, that, okay, if you have two different materials and then you want to know the manufacturability of this kind of high fidelity model can give you some insight into the behavior before you actually decide in the real practice or you invest it. This is the two extreme, I mean, nickel-based superalloy, one of which is actually has a lot of gamma palm former or secondary phase former. Another one is actually has lower. And then you will see that the behavior of this in the precipitation kinetics and also porosity level is different. So it is something dealing with the fundamental understanding on the physical property and the thermal fluid behavior that you can look at from the Proceeding of Royal Society A, paper 2018. And the plan for this has to fill up the gap of the AI that we are talking about for alloy and process design. And the future of this is actually establish some kind of high fidelity model that integrate a metallurgy and processing to advance the metric material manufacturing. And this is to link these two together. And just recently, we use this kind of principle, so-called the alloy by design computational tools to actually design a new alloy, new superalloy for additive manufacturing, which has less, how to say, crack-free alloy, for example. I mean, that is something we're proud of at the moment. You can look at a material which is online now. And in summary, I would like to say that in computational material science, especially for additive, we need to get summary statistics from the model or experiment. And then we do use AI as a kind of mining tools to improve the material and process condition for further future material development. And this one has to deal with the processing structure and property looping here, using the causal relationship in order to tell about the performance that you'll see in the real component. And another thing to do apart from the simulation is about the challenging in the modeling and also, in the experiment that we may call high throughput investigation that involves so many high level technique, for example, thermal imaging, non-destructive qualification, and a kind of high speed tomography or high speed imaging using 4D synchrotron, for example. And these of scientific and technological challenges will if we can solve it, we may advance to a next level of digital technology. by doing this, I want to summarize shortly in the last one is application of AI can also be used to simulate all these physical effects. But we need to have something to know first to link material and process relationship to establish digital material design for the next generation of metal AM. And last but not least, I want to thank all the audience today. And the last word I want to say is that this is the kind of future technology that we are looking for, the hybrid electric engine designed by Rolls-Royce or hypersonic airplane that you can take 90 minutes from London to New York, for example, or flying car here. I want to say that knowledge without technology is missing, but technology without knowledge is impossible. Thank you very much. Hi, thank you. Hello? Hello, hi.
Yes, he's still there.
Sure. I think now we are entering the panel discussion. I would like to invite Dr. Jenny Shepherd to actually host or lead this discussion, please. Thank you very much.
Okay, well, it gives me great pleasure to chair this question and answer session. And of course, I have to start by thanking all our speakers. I know as a relative newcomer to the field of AI for materials processing, I've learned a lot. There are already some questions within the chat function of this Zoom. If anyone does have any more questions, then please feel free to add them and we'll go through them as and when they come up. If you could specify who you were asking the question to, that would be great, but feel free to open it to everyone. So in no particular, well, I'll start from the beginning of the questions. So I have a question for Professor Chien Yang, and this is very much about the process of your machine learning, and the question asks, why did the study use the matrix that multiplied the corresponding input variables to convert 1D to 2D grayscale images in the convolutional neural network? So I think really trying to understand, is there a physical meaning behind the conversion?
Professor Yang, you mute your microphone. Sorry.
Okay, can you hear me?
Yes.
Yes.
Yes, we can hear you now.
Yeah. And about the enabled data, and we use the semi and supervised learning and to process the enabled data, and use this method, we can determine the enabled data, for example, and the properties of the materials we don't know with the enabled data, and with the semi supervised learning, we can predict the suitable properties of the materials, and to change the enabled data to the labeled data. So we can expand and the labeled data, and so we can make a more accurate and prediction, and with this method. Okay.
Okay, thank you very much. We've also got a question for, I guess initially for Chinapat, but it can certainly be open more widely, about
Sure.
How accurately can we calculate physical properties of materials through computation and AI, and how can we go from the micro scale to the lab scale? And actually, I would take that one step forward and say, how relevant is anything we do in the lab to actually the industrial scale?
This is quite a tricky question. So how can we measure the property that's relevant for each length scale? If I may rephrase your your simulation,
Yes.
and then sorry, your question, and then how can we make sure that this simulated property is correct, and then how can we use, this is something we need to work not only a modeler, but we have to work with experimentalists as well to make sure that the thing we observe in the modeling or the thing we use in the model sometimes is as a causal relationship. One is has to happen before another one. Like if you go to the process modeling type of scheme, you need to make sure that your property is correct first in order to give some meaningful prediction for the industry. But for the lower length scale one, it's maybe something so-called a kind of interrelation. I mean, you may do some kind of reverse calculation to get the property you want. So this one is actually it depends on the length scale you're talking about. If you're talking about the fluid length scale, you may need to use some very advanced high resolution, high spatial resolution to look at what is actually happening or going on during the process. And then you link that with the model because you somehow can measure, you cannot measure anything. You can't measure everything. You have to use model to aid your measurement, and then hence to get property. For example, I give you lately physicists will use a kind of a reverse model to predict a viscosity in a kind of severe condition once you do have some laser interaction, for example. And then this one will give you quite precise property because it's actually couple experiment and modeling. But if you are talking about industrial length scale for the component manufacture, you may not need that detail. It's made so-called macro scale property. So the macro scale property, for example, you may use some kind of tensile machine to actually test your material, and then hence you generate the property in order to feed into the model. And this one has to have an expertise of the people who has experience in solid mechanics, for example, to actually understand the behavior and hence they give some predictive capability for the specific target. And the challenge here is how can we link all this together? The way we link all this together is not well established yet. Sorry to say that. ICME community or integrated computational material science and engineering community are working on this in order to link, for example, if you want to link the interfacial energy to the melting process, this is something is still going on. It's not yet well established. But anyway, we have some people publish the work, but in order to utilize across the length scale to get really the multi-scale simulation, we still need to do more research as far as to the best of my knowledge. Yeah, thank you. I mean, other panelists may have another opinion or against my will. That's why you are welcome to do so. Thank you.
Does anyone else have any thoughts on that? Okay, so I have a question. So from my experience of really applying AI to materials processing and properties, the shortfall really seems to always be the data. So within the SUSTAIN project, it was actually really encouraging to see that industry is working together and willing to share their data. And I just wonder whether anyone has any thoughts on whether it is feasible that we can get more widespread sharing of data between industrialists and academics, and that we can really push forwards applications of machine learning with proper data sharing.
Yeah, I think Richard is not here.
Oh, is he not here? Okay.
But I may answer this. I mean, probably give some thought on this. So our world now is a digital world, digital age. So it's a charitable society. So everything has to be published and shared. And one of the thing that you may know is about the journal, that every journal promote the open access and then data in brief to share your, how to say, best data that you publish in literature. Even now, they want you to publish unsuccessful data as well. I mean, why this is important? Because if we want to use AI, we need to have a kind of very best and systematic data correction to correct all data that gives some meaningful, how to say, for the industry. At the moment, I think it's a bit scattered and random to my understanding. To overcome this challenge, I think we need to work toward the government, industrial, and university to, from now on, I mean, it will happen. Especially, I think under sustain project, I don't know much about this project, but I can say that for the green economy or sustainable metallurgy that they are working on, we're working toward this. Yeah, but I can say that the community needs to raise awareness of this kind of data publication as well. And yeah, this is my thought, and I think I think we shall see something in a positive in a positive response in next few decades.
Okay, we have one last very specific question for Professor Yang, where it asks, in slide 35, is the constitutive equation used to create the 4 neural network models?
Slide 35. Is the constitutive equation used to create?
Yeah, he's on mute again.
Yeah, you're on mute again,
you
sorry.
Unmute.
Yeah.
No, it is not for the creators and artificial neural and network. No.
Slide number 35.
Yeah, I think
yes,
he's just...
yes. No, the question is no.
No. Okay,
no.
no.
Okay, that's a nice easy answer.
Okay, yeah. Okay, yeah.
The answer is no.
Okay, sure. Yeah, I mean, yes, thank you very much.
Okay.
Yes, thank you. And another question, regarding the applications of AI to materials, is there a certain threshold of error that we need to achieve before we can actually adopt the model for practical usage? And that's to everyone.
To understand the threshold or the kind of acceptable threshold of error, we need to basically understand what is the error, what is the error is for this specific process. For example, if you give me a chance to explain something in metal 3D printing, we're not going to predict something in a precise location, but we let us predict something in a broad range of the structure. For example, rather than I predict one point, I will predict kind of distribution, what is going on, and this distribution will give you or define or give you some kind of error or kind of how can we deviate from this mean value. For example, I mean, this is something people working toward stochastic finite element calculation, for example. So we need to live in the world of statistics now. If you say about error, that means we need to understand first what is the science of that problem. If you know the science of that problem, you can define the error both experimentally and computationally. Yes, thank you.